Hey guys, Miss Peterson here, and welcome to our chemistry lecture on stoichiometry, advanced conversions. In this lecture, we're going to be going over how to do three-step stoichiometry conversions that go from grams of one substance to grams of another substance. We'll also be talking about limiting and excess reagents and doing lots of example problems and looking at how we can use the mole map to help us with these conversions. So let's get started. First, let's just talk about an example, okay? In real life, sometimes we can have chemical systems that are carefully designed to give us the exact amount of product we want, okay? Like an airbag, okay? When that car crash goes off, a chemical reaction starts that produces a gas that inflates that airbag. You wouldn't want it to be too much or too less because then your airbag could pop or it could not inflate enough and it won't be effective in protecting you during the crash. Okay? That's an example of like a carefully designed one. But if we're talking about something rusting or baking a cake or any other chemical reaction kind of just going on in the world, it's not always going to have those perfectly balanced amounts. Okay? And it's not that the reaction itself changes, okay? The mole ratios in our balanced chemical reactions are what they are. It's just we end up with some limiting and some excess reactants, okay? We're going to look at one of these types of problems and solve it through three separate one-step conversions to make sure we understand what we're doing, and then we'll go ahead and do it as a full conversion problem. Let's get started. So, in order to fully inflate the airbag without popping, they use this reaction. A chemical called sodium azide, NaN3, decomposes into sodium and nitrogen gas. And it says in order to fully inflate the airbag, 96.1 grams of N2 gas must be known. It says how many grams of sodium azide should be used. So this one right here is going to be my known, and the grams of sodium azide is my unknown. Now, anytime we see grams in a problem, what do we know we're going to need? We're going to need that molar mass. So let's go ahead and find our molar masses to start. I like to find them and just write them right under the compounds in the chemical reaction itself. So for sodium azide, sodium, molar mass of NaN3. Okay, we got one sodium, which has a mass of 22.99. And then we got three nitrogens, which each have a mass of 14.01. So when we add that together, 3 times 14.01 plus 22.99, we get 65.02 grams per mole. And then sodium is just sodium. So on the periodic table, it's 22.99 grams per mole, and then N2 is that 1401 times 2, so 28.02 grams per mole. Okay, so what language is our chemical reaction written in? Okay, when we say something like 2NaN3, what does that mean? Well, it means moles, okay? This reaction reads 2 moles of sodium azide decompose into 2 moles of sodium and 3 moles of nitrogen gas. Moles are the language that our chemical reactions are written in. So first thing we got to do is convert to moles. So we're going to start with our known, that 96.1 grams of N2. And since we're talking about 2 different substances here, we want to be really careful and put the units with our numbers and put what substance we're talking about to make it really clear. And then how do we convert from grams to moles? Molar mass. So we got 65.02 grams is 1 mole of N2. So we got 96.1 divided by, is that the molar mass of N2? No. Okay, this is why we do this. N2. So I should be using the 28.02. 28.02 grams is 1 mole of nitrogen gas. Okay, 96.1 divided by 28.02. And that tells me the gram units cancel out. I have 3.4 429, so I'll say 3.43 moles of nitrogen gas. So that's how many moles of nitrogen gas need to be completed to fill the airbag. So how many moles of sodium azide do we need? Well, we can use a mole ratio to figure that out. So now we're using the answer from this problem as our new known. And I know for every 3 moles of N2 that get produced, that comes from 2 moles of NaN3. Okay. So, and again, those numbers just come from the coefficients in that balanced chemical reaction. The moles of N2 cancel out, and we got 3.43. I'm just storing the number in my calculator to eliminate some early rounding. So times 2/3, so times 2 over 3, gives me 2.286, so 2.29 moles of NaN3. Yep. So we're almost there. Now we know how many moles of NaN3 that we need to put in the airbag. But that last step is we want to know grams. So we're going to go ahead and convert. How do we go from moles to grams? Molar mass. Now we use that 65.02. So 1 mole of NaN3 has a mass of 65.02 grams. So we got that 2.29 times 65.02 divided by 1, so times 65.02. And we get our answer, which is 148.6, so 148.7 grams of NaN3. Okay. So, in order to know how many grams of one substance we'll get or need from grams of another substance, we first use the molar mass to convert it to moles. We use the balanced chemical reaction and a mole ratio to relate the 2 different substances. And then we use the other molar mass to convert it back to knowns. So that's it, doing it in 3 separate steps, solving it out in between each one. We can also do this all in one step. So let me show you guys what that looks like. Okay. I'm going to go ahead and rewrite my molar masses. Oops. So I still have those. We got 65.02 grams per mole and 28.02 grams per mole and 22.99 grams per mole. Okay. So we still start with our known, that 96.1 grams of N2. And it's still the same steps. It's just solving it all out without doing each step independently. So we first convert to moles using the molar mass. So it's 28.02 grams is 1 mole of N2. Okay. And then we use the mole ratio. So for every 3 moles of N2, that's produced from 2 moles of NaN3. And then we're at moles of NaN3, and we know that 1 mole of NaN3, sodium azide, has a mass of 65.02 grams. Yep. So when we plug that all in, again, it's the same math, so we're going to get the same answer of 1. Why did I get 148 last? Did I get 148 last time? I did get 148 last time. Okay, of 148.7 grams. Okay, so again, it's the same steps, just doing it as a 1, 2, 3 all in one step rather than a 1, 2, 3 in 3 separate steps. Okay, cool? Okay, cool. Now, another trick that we can use to help us out with solving these types of conversions is called the mole map. Now, this mole map is designed to tell you which conversion factors you need to get from where you want to go. So in the one that we just did, we started with grams of our unknown, and we converted it to moles using this 1 mole over the number of grams. See that in that first conversion factor we used? Then we went from moles to moles using the coefficients in that balanced chemical reaction. And then we went from moles back to mass using the molar mass now of our unknown. Okay, cool? Okay, cool. So let's go ahead and try another problem. Okay, now same setup. Okay, very similar problem, but now it's a side airbag. So in this side airbag, we need 126.3 grams of nitrogen gas. So how many grams of sodium azide do I need? I got my known. I know my unknown. Let's go ahead and get through it. Okay, we got our steps. So we'll start with the 126.3 grams of nitrogen gas. We'll convert it to moles using the molar mass of our known. That 28.02 grams of nitrogen gas is 1 mole. And then we know we get 3 moles of nitrogen gas from 2 moles of sodium azide. Okay, so just a quick unit check, just so you guys can see where we're at. The grams of nitrogen gas have canceled out. The moles of nitrogen gas have canceled out. And we're at moles of sodium azide. But we want grams, so last step to go from moles back to grams is that molar mass of our unknown. So we know that 1 mole has a mass of 65.02 grams. 1 mole of NaN3. Okay, so we got 126.3 times 2 times 65.02 divided by, and then I'm putting it in parentheses, 28.02 times 3. And we get that we would need 195.4 grams of NaN3 in that side airbag. Okay, cool? Okay, cool. Let's try another one. Let's try a different path on that mole map. Yep. How many grams of NaCl can you get from mixing 0.050 liters of 2 molar HCl with excess NaOH? Okay, so what this problem is telling us is that there's plenty of NaOH around and that the HCl is going to be our limiting one. So we don't need to worry about the NaOH, okay? We're on the HCl. And we're trying to get from liters of an HCl solution to grams of NaCl. So let's look at that mole map again. Okay, so our known is our liters of our solution. So we're really starting down here at the volume of solution. And we're trying to get to grams of salt. So we're trying to get up here to mass. So the steps that we're going to be using is first, we're going to use the molarity. And they told us it's a 2 molar solution. So we'll do the number of moles over 1 liter to convert to moles. Then we'll relate the moles to moles using those coefficients in the balanced chemical reaction. And then we'll use the molar mass to get back to mass. So let's go ahead and try it. Okay. Starting with our known, we got 0.050 liters of our HCl solution. Now, as we saw in the mole map, the first step is molarity. So for that 0.05 liters, I know that 1 liter of that solution contains 2.0 moles. That's what that 2.0 molar means. Okay, moles of HCl. Then it is a 1-to-1 ratio. Okay, for every 1 mole of HCl, I get 1 mole of NaCl, okay? Again, using those mole ratios. And then we still want to get to grams, so last but not least, I need the grams, which means I need the molar mass of NaCl, which is 22.99 plus chlorine is 35.45. So you add those together. And again, those are the masses from the periodic table. And we get 58.44 grams per mole for that NaCl. So 1 mole of NaCl atoms has a mass of 58.44 grams. Okay. And then our liters cancel out, our moles cancel out, our moles cancel out, and we're left with grams. We plug it into our calculator, and we get 5.84 grams of NaCl. Okay. So, are you seeing where these conversion factors are being pictured on the mole map? Okay. And how you can use that to help you set up problems? Cool. Do we see the canceling of the units to make sure the units work out? Okay. Those are the tricks that we need. Let's go ahead and do one more example and tie in this idea of limiting an excess reactants. So we have aluminum and copper chloride producing copper and aluminum chloride. This is that reaction we did at the beginning of the unit where you have a blue solution and you put the aluminum foil in it and it turns into a red solid. So it says if I put 1.2 gram piece of aluminum foil in 1 liter of 1 molar copper chloride, how many grams of copper could be produced? So this is a situation where we have two knowns, okay? We have two different ingredients that we know how much we have of. But what we don't know is which one's going to limit how much product we can make, which one's going to limit how many sandwiches we can make. So let's go ahead and figure out how many moles of each reactant we have. Now, we know we have grams and moles, so I'm going to go ahead and write our molar masses. Aluminum has a molar mass of 26.98 grams per mole. Copper chloride will be copper, which is 63.55. Just write that right now, 63.55. And then copper chloride is 63.55 plus 35.45 times 2, which is 134.45 grams per mole. And then aluminum chloride, I don't think we're going to need the aluminum chloride, but we'll go ahead and find its molar mass anyways. It's 133.33. So let's figure out how many moles of each reactant we have, because sometimes the limiting reactant's obvious, like we have way more of one thing than another. So starting with the aluminum, we have 1.20 grams of aluminum. So if there's 26.98 grams of aluminum in 1 mole of aluminum, okay, we only have 0.044 moles of aluminum. Now, for the copper chloride, we can probably do this one in our head. We have 1 liter of a 1 mole per liter solution, okay? AKA, we have 1 liter, and then it's 1 mole per liter. So we have 1 mole of the copper chloride, okay? Basically, we have 100 more times copper chloride than we have aluminum, okay? Let's see, 1 divided by 0.044, 22 times. Okay, we have 22 times more copper chloride than we have aluminum. And we only need a little bit more. We only need it's a 2 to 3 ratio. So we need 1.5 times as much. We definitely have that. So we know that the aluminum is going to be our limiting reactant. Okay, that's the one that's going to limit how much product we can form. So let's go ahead and see how much product are we going to form. Okay, so we'll start with our known, that 1.20 grams of aluminum, because that's the one that's going to limit how much copper we can form. Now it is a gram to gram conversion problem again. So I'll go ahead and throw the molar masses here for our known and our unknown. So first I convert the aluminums. Grams is 1 mole of aluminum. And I know for every 2 moles of aluminum that react, I get 3 moles of copper. Okay, and that's what we're looking for. But we're looking for grams. So I know that 1 mole of copper has a mass of 63.55 grams. So I have 1.2 times 3 times 63.55 divided by, and I'm putting it in parentheses 26.98 times 2, close the parentheses, and we get 4.24 grams of copper. Yep. Okay, cool. So, how much excess? Well, to figure out that, we need to figure out how much of our copper chloride was used up in reacting with the aluminum. Okay? And we can just do it in moles because we already know our starting moles. We had 1 mole of copper chloride to start. So how much is going to react? Well, let's go ahead and go back. We got that 1.2 grams of aluminum. Convert it to moles, which I guess I could have just had this number stored and known how many moles it was and skipped this conversion factor. But we know for every 2 moles of aluminum, it reacts with 3 moles of the copper chloride. Okay, so I got that 1.20 divided by 26.98, that 0.044 moles of aluminum times 3 over 2, and we get 0.0667 moles of copper chloride will react. Okay, so if they reacted, they're no longer going to be present. So we can subtract that from our original amounts, and we find out that we will have 0.93 moles of copper chloride left over. Okay, cool. Okay, cool. And that's it for our advanced stoichiometry.